All right. Once again, ladies and gentlemen, today we're going to be discussing non-part 2, which are polar graphs. So in non-part 1, we talked about points in a polar plane. We talked about some very simple shapes in a polar plane, like circles, which are complicated in a rectangular plane, but it's extremely simple in a polar plane. It's just r equals and then whatever the radius is. And then we talked about lines, which is just theta equals some value. And then we talked about simple curves, like r equals 2 theta. Remember, that was the spiral shape that we discussed. Okay, so a little bit more complicated expressions. R as a function of theta in the polar plane. And remember, the polar plane works like this. So you've got two axes. And the distance from the center is the r. So r equals the radius or the distance from center, where the origin, of course, is the center. And theta is the angle to the horizontal. So you're going to have successively larger concentric circles. Let's see. Let's do it this way again. And they need to have, each one unit larger radius than the one before. It's hard to do that perfectly by hand, but you guys get the idea. So any point on this circle has 1 unit of radius. Any point on this circle has 2. Any point on this circle has 3, and so on. Angles to the horizontal start here at 0. So just like the unit circle or any other standard angle to the horizontal, this is 0, 90, 180, 270, 360, and so on. But remember, we can go in either direction. So when I say 270, I could also describe that with negative 90. And on the quiz, which you'll be taking soon, I threw some of those negative angles at you to make it more challenging. So make sure you understand how negative angular motion works. But this is 0 degrees here at the horizontal, and 90 degrees, 180, etc. You guys get the idea. And then this is 1 unit of radius, 2 units of radius, 3, 4, and so on. All right, so let's graph a little more complex polar relationship. So notice here I've only got 2 circles, 2 units of radius. That's all you'll need for this. Again, it's less than ideal to sketch it by hand. Usually I print out a sheet of polar graphs, but the copier's been down, so we're just going to have to make do with our by hand sketch. So I'm going to pick some angles here, some thetas. R is a function of theta. Theta is the independent variable, in other words, the one we pick. And then R is our dependent variable, in other words, the one that is fixed by that choice. So we choose theta, and then that fixes R to a certain value. Do you see what I mean? It's like this is analogous to the X in the rectangular plane, and this analogous to the Y. We pick an X, and that tells us what our Y is. Here we'll pick a theta, and that'll tell us what the R is. So I'm going to pick some thetas to help me understand what's going on with this. So I'm going to pick 0 radians. I'm going to pick pi over 6 radians. I'm going to pick pi over 4, pi over 3, and pi over 2. Now you will notice those are all the angles from quadrant 1 of the unit circle. So these should be real easy for you if you remember the unit circle. All right, so I picked 0, pi over 6, pi over 4, pi over 3, pi over 2. Jesse, what's cosine of 0?
Cosine of 0
Mm-hmm.
be 0.
No. Cosine is the x-coordinate. All right, so let's go back again to the very challenging unit circle. Remember I told you guys, you've got 0, you've got pi over 2, and then we've got these 3 rays. And for every point on the unit circle, the x-coordinate is the cosine of theta, the y-coordinate is the sine of theta. Quadrantal angles are real simple here. And then the ones in between, which are pi over 6, pi over 4, pi over 3, or 30, 45, 60 degrees. There's this real little simple pattern to it. They're all fractions over 2. And then you just go 1, 2, 3, 1, 2, 3. Put a radical over everything that's not a 1. So you've seen me do that maybe 20 times now. If you can't do it by this point, I'm not sure what to tell you. You're just intentionally refusing to learn it, would be my only assumption. So let's try again, Jesse. Remember that the cosine of theta is the x-coordinate, and we're looking at 0 radians. So what is it?
For cosine of 0,
Yes.
pi over 2.
Okay. I asked you for the cosine of 0, and you gave me an angle. You see how completely off base that is? The cosine is a ratio. It takes an angle for its argument, and it spits out a ratio. So 0 radians is the angle that we're plugging in to cosine. The answer should be a ratio between -1 and 1. So try. 1 is correct. Now, based on that conversation, we've got to review this. So if one more person has that level of difficulty, I'm going to stop what I'm doing and give you a unit circle quiz. And I'm going to do that until you get it right. So I suggest nobody else pull that on me. 1 is the correct answer. Holden, what is the cosine of pi over 6?
Radical 3 over 2.
Good. Rachel, what's the cosine of pi over 4?
Radical 2.
Good. And then Bristol, what's the cosine of pi over 3?
1/2.
Good. And then what's the cosine of pi over 2, Rowdy?
Cosine of pi over 2 is 0, right?
Yes.
Okay. I thought I messed that up, but I was right.
No, you're right. You guys have avoided my wrath for the moment. So here we have some points, some polar points, where those work differently than rectangular points. So at 0 degrees for the angle, I come out 1 unit of radius. So that's here. At pi over 6, which is this first radial arm, I come out the square root of 3 over 2. Now we probably need to think about the decimal values because it's going to be difficult for you to know how far that is without converting it to a decimal. So that's about 0.86 or just less than 1. So we'll go something like that. Square root of 2 over 2. It's about 0.7. So that's on this 45-degree arm. So a little past halfway. And then radical 3 is 1/2. So that's about halfway. Radical 2 is 0. So you see how that's a semicircle? And I could probably infer what the rest of the graph would look like, but let's go ahead and continue on. So let's go to the values in Q2. So we'll do 2 pi over 3, which would be this next radial arm. And then 3 pi over 4. Sir.
I was cutting through,
Yeah, come on.
but you know, this exercise is not Area 51.
It sort of is. You know, 2020 is a crazy year. The Navy puts out, you're talking about Area 51, the Navy puts out video of UFOs.
No.
Yes, the Navy released it from the point of view of a Navy pilot and said, this is UFO. This vehicle couldn't possibly have been produced on Earth. That's the United States Navy. And everybody's like, whatever. Like, not even many news outlets carried it. It's a crazy year. Okay, so anyway, 3 pi over 4 is this next one. 5 pi over 6. And then pi. So those are the radians for these values. And remember the symmetry of the circle. Gives us the values here. Remember that how these 2 points are symmetric, but we're in Q2 where the x is negative. So that's this would be -1, 0 is what we want there. Okay. So Holden, tell me what the cosine of 2 pi over 3 is. Good. Rachel, what about cosine of 3 pi over 4?
Negative radical 2.
Excellent. And then Jesse, what about the cosine of 5 pi over 6?
Negative radical 3 over 2.
Good. And then down here at pi, Colin, what is the cosine of pi?
-1.
Good. So if we start putting in these values, 2 pi over 3, remember how negative radial arms work? They go away from the angle. So if I come over here to 2 pi over 3, I need to go negative 1/2 units. And then if I go to 3 pi over 4, which is here, I need to go negative radical 2 over 2, which you'll remember was about 0.7. And then if I come to this arm, 5 pi over 6 here, I need to go negative radical 3 over 2, which you'll remember was real close to 1. And now you see probably the entire shape. A little circle over there. So if I use the calculator to do this, so if I go to y equals, clear this out, put in cosine theta. Now remember, our mode needs to be polar for the function, and our angle input needs to be in radians. So make sure both those things are true. And we have to set the window up carefully. 0, we went from 0 to pi, so we'll replicate that here. And the theta step should be positive about 0.1. Now, if I did this negative 40 to 40, you see how it would just be a little tiny speck, and we wouldn't even know what's going on. So let's do like we did here. So negative 2 to 2, and negative 2 to 2. It looks elliptical, but it's actually a circle because that screen is rectangular, not square. But all rectangles are squared, or all squares are rectangles, but not all rectangles are squares. This is a rectangle that has a longer x-axis than a y-axis. That's why you see that shape kind of stretched out. Okay, so Polar graphing relies very heavily on your knowledge of the unit circle. And really, 2020, for the last like 12 or 15 years, the order of the day has been to learn and purge. You learn for the end of course test, and then you just forget all that crap and start fresh the next year. That's not really the way advanced mathematics works. Everything's scaffolded, built on previous learning stuff. This is a pretty fundamental level of that scaffold. So if it's weak, you need to go back and revisit it. Okay, so now let's talk about r equals sine theta. So this time we're talking about sine of theta, which is the y coordinate from the unit circle. I'll use the same points. So we'll do 0 radians, pi over 6, pi over 3, pi over 4. I've got those backwards. So we won't go in order. New sun was up. Pi over 4, pi over 3, pi over 2. Okay, so going along the unit circle, we're talking about y coordinates now. So this is not going to be the same as the previous answer. Roddy, what is the sine of 0?
0.
Good. Colin, what's the sine of pi over 6?
1/2.
Excellent. Jesse, what's the sine of pi over 4?
Radical 2 over 2.
That's what I'm talking about. Rachel, what's the sine of pi over 3?
Radical 2 over 2.
Very good. And then, Holden, what about the sine of pi over 2? See, that's all it takes. I just got a bar catch over there. And you fall right into line. All right, so 0, 0 is here. And then pi over 6 goes to 1/2. That's about there. Pi over 4 goes to radical 2 over 2. Remember, that's about 0.7. Pi over 3 goes to square root of 3 over 2. Remember, that's like 0.8 something. And then pi over 2 goes to 1. So once again, see how that's a little semicircle? So if we go down into Q2, talking about the y coordinates again now. Crystal, what is the sine of 2 pi over 3?
Negative radical 3 over 2.
Yep. You almost went sideways with that negative business, but the sine is positive in Q2. The cosine is negative.
Oh, yeah.
Rowdy, what about 3 pi over 4?
That should be 2 over 2, or radical 2 over 2.
There you go. Jesse, what about 5 pi over 6?
1 over 2.
Good. You see the symmetry here? So, Rachel, what about sine of pi?
Is -1.
Okay, so once again,
Sorry.
the sine is the y coordinate. The sine is the y. The sine is the y. 0 is correct. Okay, so let's plug these points in. 2 pi over 3 is this radial arm, and we need to go almost 1, but not quite. 3 pi over 4, this radial arm, we need to go about 0.7. 5 pi over 6, this radial arm, we go about 1/2. And once again, we see this other half of the circle. If we graph this on our calculator, we'll graph it in conjunction with what we've already graphed. So I'll leave the cosine in place. You'll see that. So just a good little mental note to make. The graph of the sine of theta is up above the what we call the x-axis in the rectangular plane. And the cosine of theta is to the right of what we call the y-axis in the rectangular plane. Just to, if I were you, I would commit those shapes to memory. You might see them again on a quiz or a test. So a little more complicated now. Let's do one that has a more complicated expression. One minus 2 cosine theta. And notice I've got 3 circles here because there's a little bit of difference to this shape that would make it challenging to do with small graph. All right, so once again, we're going to pick some angles. Let's pick 0, pi over 6, pi over 4, pi over 3, pi over 2. Now, this is 1 minus 2 times the cosine of our input angle. So what is the cosine of 0, Jan?
That would be 1.
Good. What about the cosine of pi over 6, Holman?
Right in 3 over 2.
Very good. You guys seen this pattern yet? It's not hard. Jesse, what about the cosine of pi over 4?
Radical 2.
Jesse, what about the cosine of pi over 3?
1 up 2.
Good. Wanted to see if you went to sleep after I ask you one. You never know where I'll go next. Bristol, what about the cosine of pi over 2?
0.
Yes, good job, buddy. So if we evaluate out these r's, give us some polar points. 1 minus 2 is negative 1. 1 minus the square root of 3, that's going to be a decimal, so let's just find the decimal value. 1 minus the square root of 3, it's going to be like negative 0.7. And then 1 minus the square root of 2, it's about negative 0.4 to the nearest tenth here. And then 1 minus 1 is 0. 1 minus 2 times 0 is 1 minus 0, or 1. Let me just double check myself here. Actually, there's a pretty easy way to check ourselves. Use the calculator. 1 minus 2 cosine theta. If I say trace 0 is negative 1, that's right. And then pi over 6 is, it gives us an x and a y here. It doesn't give us an r. Well, I'll assume that's correct. So let's grab it. We know what the shape's like anyway, now, so we'll know if that's right or wrong. 0 goes to negative 1, that's here. We're away from the angle if the radius is negative. Pi over 6 is negative 0.7. Pi over 4, that's this radial arm right here, is negative 0.4, so just less than half. Pi over 3 is 0. And pi over 2 is 1. So let's see, it's going to kind of do that funky thing. And if we let theta go on, it would spiral around and make some interesting shapes. Polar graphs. If you want to impress somebody with the TI calculator, as if that's possible, polar graphs is probably the way to go.
I saw somebody that like downloaded games on there. It's like they had like Crash Bandicoot and they were playing it in class.
Yeah, that used to be much more of a thing than it is now. Now, of course, kids have their phones,
Yeah.
but there were like Super Mario clones on the
like,
TI
you put it all on
calculator.
the tablet.
Kids used to go wild for back in the day.
Yeah, but like the new ones with like the electronic screens, you have like cars and stuff, like the new ones. You got like actual digital like games and stuff on it. It's weird.
Before computer programming became a class here, I sponsored the computer programming club. And one year we had a guest for the club that was a programmer for TI calculator software. And he made a video game on the TI calculator from scratch, right in front of us in about 15 minutes. It's extremely impressive. And it was, like a little character jumping, platforming. I was amazed that he could do that. It goes to show, even these arcane interfaces can be manipulated if you know what you're doing. So we're going to next talk about something called roses. You like it when people give you roses? Okay, I'm going to give you a rose. You can keep forever on your calculator. So they look like this: A cosine B theta or A sine B theta. And they've got a really specific and interesting shape. So you'll find these on page 546. Okay. There are plenty of other interesting polygraphs. These are the ones I thought were most interesting. So there are some interesting things about the roses. First of all, A is how far the rose comes out from the center. This is a 5, for example. You would have 5 units from the center in each direction for your rose. So A is the size, the radius of the rose, how far it comes out from the center. And B affects the number of petals, but not in a way that's easy to predict. It's pretty complicated, actually. So the way B affects the petals is it has B petals if N is odd, and 2 N petals if N is even. N petals, or B petals if B is odd, 2 B petals if B is even. So let's play around with this a little bit. So if I go here, and I'll erase what we just put in there, I'm going to put in, let's say 5 sine 6 theta. And I need to change my window a little bit. 2 pi. And then I need to go, let's go at least 6 units here. My goodness, it's hot in here. It's ridiculous this time of year. Okay, so look at this, Jesse, and tell me, how far is it going to go out from the center of the graph?
5.
Good. And then, Rachel, can you tell me how many petals it would have?
It's gonna have 6 petals?
Well-
Wait, what exactly do you mean?
Look at these 2 statements.
Oh, even. Right, because.
It's even, so how many petals would it have?
even, it has six, right? Because there's just six in the.
Okay.
Wait,
So B petals, if B is odd,
yeah.
2B. So what's 2 times B?
Is the
12.
Okay. I get it now, sorry.
No. Yeah, there we go. Pretty interesting.
So, please tell me we don't have to draw that, like. on
No,
paper.
do you notice I did this one by calculator?
Well, I'll just-
I will always do roses and other complicated public shapes. In fact, we're basically done doing them by hand at this point. Everything beyond this is more complicated and best done through the use of technology. Let's do another one here. So let's see. Oops. So Bristol, tell me how far out from the radius this one, or how far out from the center this will go. 2 is correct. Jim, what about the number of petals? 3 is correct. So it'll be quite a bit simpler than that previous shape, won't it? Like, looks like a fidget spinner or something. What about, let's see if I do this. Let's do 5 sine of 16 theta. How many petals will this one have, Holden?
32.
It's going to be a mess, isn't it? You probably won't even be able to tell them apart.
Oh, yeah, that's easy.
It'll just look like a starburst.
Actually, it looks really cool. Do more, do like 100.
Well, eventually, we're going to run into the pixelation limit of the calculator. But if we do a whole big bunch, let's just say 50 here.
Is it like create like a circle? It's just gonna be.
Yeah, it's kind of hard to distinguish after a certain point, and I need more
See now?
theta because it's not going to hit those other ones. So let me change this to like 30 pi.
Like I'm wanting a solid shape, like a full circle.
This will be close.
It looks like you're going in a hybrid mode.
Yeah, this will be close.
What did you change to,
The window, I changed the theta max to 30 pi.
Oh, it would definitely.
This is the birth of the sun.
Somebody do this.
It is the beginning of our universe.
Oh, we do like 5,000 on your calculator.
Yeah, you'd be
I
waiting a
would
while.
rather not use my calculator.
Just
Catch
set it
up.
on. Just drains the batteries.
Instantly.
That is really cool.
So that's a rose. And again, if it were possible to impress someone with a calculator, this might be the way to do it. So you get some pretty interesting shapes still going there. There are some other ones. There's what's called limicons or cardioids. Those are interchangeable terms. You've already seen the circles, which we did with r equals sine theta or r equals cosine theta. But the limicons or the cardioids, I can do one of those for you real quick. We won't bother with a lot of definition. Still going. Can I break it?
It's still.
There we go.
But you can break it up.
Yeah, second and on, I think, breaks it, I think, on most calculators. So a limicon, if you look at that page, is A plus or minus B cosine theta. So we can do 5 plus cosine theta. And if we don't need that much, let's go 4 pi would be plenty.
So
Yeah. Some of them look like that. B sine theta. It says A minus B sine theta is more interesting. So let's do this one. Yeah, kind of like a heart.
No,
I'm not saying hard.
that. It's just like curve.
Well, it's,
What was your equation there? 5 minus sine theta?
yeah, I'm gonna change
5
it.
minus 3 sine theta.
Let's change it to 2 and see what happens. And it's flatter that way, isn't it? So we need a bigger value in front of our sine term. If I change this to 4, let's see what happens. Ooh, that's more distinctly heart-like, isn't it? And I think if we reduce that 5 to about a 3, let's see what that looks like. Yeah, that's getting there.
You gonna send that to your girl?
Valentine's Day's coming up
Or
in
no,
a couple
Make
months.
you a heart like that.
Never too early to start
I
planning.
made you a heart on my TI 83. Like that.
I would say they would be pleasantly surprised.
Oh,
Both your nerdiness and
Plus,
romantic capacity.
wow, get away from me. This is all done.
That might also be a reaction, Jesse, I don't know. So that's a cardioid, and it's also called a lemicon. Then there are things called lemniscates. So this one is sort of like that. Lemniscates are pretty cool. Let's see here. Yeah. These are a squared cosine or sine of 2 theta. So let's do 2 squared cosine of 2 theta. Hopefully this shape will look like it does on the thing. That's kind of just like a rose, isn't it?
Pretty much.
Oh, should be plus or minus the square root, sorry. Because it's r squared, not r. Let's see what that looks like. Supposed to be an infinity symbol. Yeah, I guess it kind of is. A little weird looking. And then we've already talked about the spiral, so you guys know the spiral. Okay, so any questions about anything we've discussed? Or thoughts or comments? Okay, cool. In that case, you would complete the following for me. I appreciate it. Oh.